Hi everyone and welcome to this video and the full stack machine learning mastery course, and we have already talked about machine learning fundamentals, and we have also talked about linear regression in machine learning, and we have also developed linear regression from very scratch and also with the help of sklearn. And I hope that you got better intuition about all those kind of stuffs, and if not, please watch my previous video because this video is related to all my previous courses, so to all my previous videos in this course. Okay, so be sure to follow this in sequence. But if you are an intermediate, if you're come from a random video, you're feel free to continue with this video. Okay, but you should have a basic prerequisites of linear regression and gradient descent and cost function. Okay, so now in this video what I'm trying to do is I'm going to try to explain you is about polynomial regression and ridge regression. So we'll talk about what is a ridge regression just in a second, but we'll talk about two topics for today, and in the next video we'll talk about lasso regression, elastic net regression. Okay, so let's talk about actually this is an overview of what we're going to learn and what we are actually going to learn. First of all, let's talk about polynomial regression. As you know that in linear regression we have a data which is a linear data. As we have known that linear regression is will only perform best onto the linear data, means the data is in linear, so we can fit the straight line over there and then we can get a good prediction. But in this case, this is an example of polynomial data, not a non-linear data, I could say non-linear data. Okay, so this is an example of a non-linear data, and if you fit the straight line over here, this is the very bad prediction, because you can see here that we have predicted here but the actual value is here, or you can say here, so it is very bad. But this is possible this is possible with the ridge regression, and ridge regression is often called, the polynomial regression. I'm saying polynomial regression is a type of linear regression, but polynomial is for non-linear data. Okay, so what does polynomial regression does is it will make a polynomial or quadratic like this, and this is kind of a quadratic kind of figure, I could say quadratic figure, so it will form a quadratic figure. Okay, so it may happen that in complex means you have a very complex data, and if you fit it the straight line, this will not perform well onto that data. So surprisingly we can use the linear model to fit the non-linear data. So polynomial regression is a type of R where we can say the linear model, and with the help of this linear model we can actually predict we can actually go with non-linear data. Okay, so we'll see some implementation here. So what is the way for doing that? So there is a simple way to add the powers onto the feature weights, onto the new features. Like let's say this is our kind of data for house price prediction, and this is a non-linear data. Okay, so this is our non-linear data, so it may happen that this is the number of bedrooms, number of floors, number of fans. On the basis of these features we are going to predict the price of the house. Okay, and again I'm taking this just an example, this is not a real example. Okay, so what we do, we add powers to each and every features. We simply add the powers to each and every features. Let's say you want to add 2-degree polynomial or a 3-degree polynomial. So if you want to add 2-degree polynomial, you can add 2 here, or if in 3 you want 4, I could say if you wanted a 4 you can write 4, just like this you can go on. Okay, so what we do, we add powers of each feature, so x1 squared, then we have x2 squared. This is the degree of the polynomial. Okay, but in this case we'll be using this quadratic equation y equals to ax square, and a is the coefficient, so x square is the quadratic equation, is the power, we can say. Okay, so this is very simple technique to do that, but what we do, let's take a look at the implementation part just now, and if you've not understood, I'm going to explain one more time. So what we are going to do, let's say these are our features x1, x2, x3, and we have to give this feature as an input, and we are going to get the output. This is our y hat. Okay, so what we do in a non-linear case, we add the powers to every features. In this case we have added 2. Okay, so what is the general implementation will look like? So first of all, we'll generate some linear, non-linear cooking data. So we have generated m, we have generated x, and again m here is the number of training examples. M is number of training examples, and again number of training example is the size of a training set. So it may be there's a size 100 rows. Okay, so this is the number of training examples into that data, and in that we have an x and y, and here x is the input value and this is the output value of the particularly for x. And you can see here that we have added a 2-degree polynomial. This is 0.5 times x squared plus x plus 2. This is very much similar to this equation, as I can show you here. This is very much similar to y equals to x squared plus bx plus c. Okay, so we have generated some non-linear cooking data, and then what we will do, then there is a library in sklearn which is often called the polynomial features and sklearn.preprocessing. It is a pre-processing step. So we will degree 2, and there is some hyperparameter. Which degree do you want? We want 2 degree, means the power, or 3 or 4, whatever you want. In this case I will give 2, include the bias, no, and I don't want to include the bias. And then we'll use fit transformer. This is called the transformer that will transform our x to, what I can say, this one, ax plus bx plus c, to ax squared plus bx, I could say bx plus c. Okay, so it will transform this. This is I'm taking just an example. Okay, so this fit transform the data, and then we can fit our linear regression onto this x polynomial. We can fit this linear regression onto this x poly instead of using this. Okay, so this is the pre-processing technique that we will use, and then after pre-processing the nonlinear data, or we can say a new variable x poly, and we can use the linear regression onto that x poly, and y would be the same. Okay, so this is our general step. Let me run this, and now we have trained our model. This is a very simple implementation of polynomial regression. Okay, so we have now a very good kind of understanding of linear regression, and I hope that you had also understand the polynomial regression. Again, I'm going to explain one more time. It will be beneficial for you. Is what we are in polynomial regression do is, let's take an example. We have a nonlinear data, and nonlinear data we can't fit the linear model, or we can set a straight line. So what we do, we transform our nonlinear data into the power or the polynomial terms, and then we can use the linear model over there. Okay, so this is what we are doing till now. Okay, so as you can see that if you're following my course, you might be familiar with the two famous techniques known as the overfitting. Techniques in the error, it is known as the overfitting and underfitting. So it might happen that your model occurs overfitting or underfitting. So let's talk about overfitting. And in the first video, or the lecture 1 of this kind of course, we have already talked about overfitting and underfitting in detail, but again I'm going to talk about it in detail here only. Okay, so overfitting occurs when our model generalized well on the training data but fails to generalize well on our testing data. Okay, so here you can see that here we have our overfitting and here we have our underfitting. Okay, so what does overfitting does? It fails to generalize well onto new example, but it generalizes well onto the training set, but it fails to generalize well onto the testing set. What does it mean? So we have trained our model onto this training set. It performs very well onto this training set. Whatever we give the example, it will give it an accurate prediction. But with the new example, if you give new example, it will perform very badly. It will not give very accurate predictions. So this is called overfitting. Okay, to reduce overfitting, we use a regularization technique. Okay, so we use a regularization technique. Again, I'm going to explain overfitting. Okay, so here we have our, let's take an example, this training data. This is our training data, and what in overfitting, our model works like this. And in this way we can identify it as overfitted. Means it will perform very well on the training set, but will perform, if you give the new value x, this will perform very badly onto that new example. Okay, so to reduce overfitting, what we use regularization techniques. There are a lot of regularized linear models. Okay, so what is the best problem, as a solution to the problem is regularization. Okay, so there are kind of, I could say, Ridge, Lasso, Elastic Net, and these three models or linear models is the regularized linear models that we often use. Okay, so the first regularized linear model, we have Ridge Regression, and the prerequisites for extending up is that you have watched my previous video. Although if you're new, kindly watch that. It is a gradient descent you should know. J of theta means the cost function you should know. Okay, so in Ridge Regression, what we do, we add a simple term, we add a regularization term at the end of a cost function, except theta 0. And you might be thinking, hey, what you have told till now. So let me explain one more time. So in Ridge Regression, what we do, we add, this is our J of theta, we add the regularization term, which is often called alpha 1 upon 2 I equals to 1 all the way down to n, it is n, theta 2I. Okay, theta squared I. So this is our regularization term. You can see here, this is our regularization term, I could say, and this is how you should see here. Like, we add a regularization term at the end of our cost function, and then we can and our cost function will look something like this. And our cost function will look something like this. This is our cost function that we have already studied, and it is just taking out the difference between the actual value and the predicted value and the actual value, and then summing it all up. And then we add a simple regularization term, alpha 1 upon 2I equals to 1 all the way down to the n, theta squared subscript I. And here theta squared I, here I will be for I equals to 1 all the way down to the n. Means theta 1 all the way down to the theta n. Okay, so here n is the number of features, means x1, x2, x3, or you can say the number of bedrooms, number of bathrooms, number of floors. These are equivalent. Okay, so what we do, we add a regularization term at the end of cost function, but we leave the bias term theta 0 because we don't want to reduce the bias term. Because what does regression does? It reduces the theta value as much as possible. Okay, the weights, it reduces the weights, so we don't want to reduce the weights of theta 0. So we start with I equals to 1 to theta n. So it will go 1 upon 2, then we have a theta 1 all the way down to the theta n, and we take out the bias term explicitly. Okay, so we take out the bias term explicitly. Okay, so let's take a look at what we are doing. Okay, so what we have done, we have taken out theta 0, we have taken out, this is our for theta 0, this is for theta 0, and we've taken out theta 0. We will do explicitly all the things for with respect to theta 0, and then here for theta 1 all the way down to the theta n. Here n is the number of features. I'm going to write a notebook. Okay, the number of features, and then we are just getting our cost function. Okay, so one thing more that I want to note here, that if we put, it is very kind of more, if you get a lot more large training set. So if we use this, we have around 1:1 lakh features. It will take a lot of time, or we can say 100. It will even take a lot more times. So what we'll do, we will put this theta 1, theta 2, theta 3, all the way down to the theta n, into the feature vector w. So now it will theta 1, theta 2, all the way down to the theta n, and I will put all those thetas or feature weights into the parameter vector or feature vector w, and then the regularization term is simply thus. We will not use this. Instead, we'll take out a norm of or to L2 norm of our regularization, or against a w of our parameter vector. So what we are doing, we are taking, this is simply the L2 norm, or we can say the norm. It is taking the length of the vector, and this is the L2 norm. You can search on the internet about the same. What is L2 norm? This is a simple one-line kind of explanation. Just search on it and then come back. Okay, so this is what we have done till now. We have put in all our n into the vector w, and then we are taking the L2 norm of that instead of going with each and every example, but leaving theta 0 again, but except theta 0. Okay, so what does gradient descent will look like for Ridge regression? So the gradient descent will be the same, because in the cost function we will explicitly take for theta 0, because our cost function is now this one. Our cost function is this one, so we'll explicitly take for theta 0, and we will take the partial derivative of our cost function theta z. Okay, we will explicitly j all the way down to the n. We'll explicitly take the partial derivative, because our cost function j of theta is equals to this. Okay, so it will eventually update our parameters, so like that. Okay, so and at last we'll update our parameters with alpha value again. Alpha value I've already explained you, and again I'm going to explain the rate at which we are learning, or the rate at which we go, because this is our cost function, and our theta is here, so at which rate it should reach out to the global minimum. Okay, so this is our procedure for developing a full stack Ridge regression for Ridge regression. First, we just added only this term, this regularization term at the end of our cost function, and then again doing the same things. Okay, so and I hope that you got better intuition about all. I will make a class Ridge, and in that class again I hope that you might be familiar with the object-oriented programming in Python. Okay, so don't focus on here only, just focus on what I'm writing and code me along. And before that you can code by yourself. It is just the same, but just wait, we are developing the same things. Because in program assignment you will be getting the skills what is required for all these things. Okay, so first of all I will do the same self, and then it will take learning rate. I will take alpha, and then it will take iterations, because in kind of gradient descent we want iterations, and then it will take the L2 penalty, because we are taking the norm, so L2 penalty, and then we will do cell dot learning rate, it's alpha equals to alpha, and then self dot iterations equals to iterations, and self dot L2 penalty equals to L2 penalty. Again, you can use any kind of name here, but using this is the best practice. Okay, so this is our initial steps, and then what I will do, I will define fit, because we will call ridge.fit that will perform all the things that are required. Okay, so it will first of all we'll take out the m and n. Here m is the number of training examples and n is the number of features. So self.m and self.n, and this is simply you can either say length of y, in most of the cases works best, but it guarantees x.shape works best in all the cases. Okay, and then what I will do, I will define a predict function. I'll put down all the weights. Feature weights initialized to 0, because all the feature weights like theta 1, theta 2, all the way on theta n, we'll put that into theta 0, because we'll initialize the parameters with 0. Okay, so I will name it as a np.zeros, and this is the same as our features, because the number of features means theta 0, theta 1, theta all the way around to theta n. So these are the features of feature weights. Okay, and then we have a bias term which is often called a bias. I will put that because there is one bias term which is theta 0, and then I will self.x equals to x, and self.y equals to y. Okay, self.x equals to x and self.y equals to y. I will use a gradient descent for and then I will update our parameters. So for I in range, this will take self. I could think self x comma y. For I in range iterations. For I in range iterations, and then it will self dot update params, and we'll make update params just in a second. Okay, so we'll make update params just in a second, and then I will return self. Okay, and then I plan for making update params. So it will take nothing, it will take only self, because, and then what I will do, I will update the parameter. So first of all I will calculate the gradients. So for calculating the gradients, I have y prediction, because I'm going to take the yx. So I'm going to make again self predict function just in a second, and then I will calculate the gradients. So for calculating the gradients, what I have done is I have written the equation previously, so I will just write it down and then come back. Okay, so I have already written down this one because it takes a lot of time to write this. So I have already written down the equation. This is just taking out the partial derivatives. This one is taking out the partial derivatives, and this is updating our parameter and then returning the things. Okay, so we have developed our kind of ridge regression from scratch. So let's run this. Let's see what the error is. Okay, so we have our model, which is a ridge, which works very best. Okay, so this is our kind of simple Ridge from very scratch. Again, this is very easy. We are just self.update parameters. It is updating parameters. It is predicting here using this function. I hope that you are familiar with object-oriented programming in Python. Okay, so now I highly recommend to use this only for educational purposes, I could say, or to understand the algorithm. But in real world, I don't suggest using this your own made model, because although scikit-learn have their own, because scikit-learn is far better than this, because it is a lot of functionalities. So you must have to know about scikit-learn also have, but taking this is a very good practice to understand the algorithm from scratch. Okay, so from sklearn I will in sklearn it is pretty much easy to use that. Simply we have a SGD regressor, and this is stochastic gradient descent. And you might be thinking, hey Ayush, what is stochastic gradient descent? Just for now I will tell stochastic gradient descent means the gradient descent, but in future we will explore stochastic gradient descent, atom, RMS prop, then we have a batch, mini batch gradient descent, and that kind of thing. But SGD grader is the gradient descent like that. Okay, and then I will make the object SGD, and I will tell the gradient descent to add L2 norm at the end of the cost function. So this will add the L2 parameter or the regularization parameter at the end of that, and then I will use this reg.fit and x. This pretty much is the 3 lines of code, and we are done. Okay, and we are done, and you can run this. Let's see, it will give an error. No, it is not given an error, and we're good to go. Okay, so you taking a look at this, it's very kind of good practice, because you will understand how actually algorithm is working, and then 3 lines of code does the very far better than this. Okay, so this is for educational purposes, like do not use unreal data. Okay, some of the technical note on ridge regression: before using any regularized models like ridge or lasso, it is very sensitive to scaling, or it is very sensitive to data. So to prepare the data, and the most importantly, you have to scale your data using the scikit-learn library, which is often known as standard scaler. And if you don't know about that, don't worry about it. If you have not understand, you will understand. I will make a full video on the feature scaling, which will explain. But for now, this is a technical note you should remember. Okay, but in future we will be definitely working on what is a standard scaler and what's feature scaling. Okay, so this is our whole kind of model, and I hope that you enjoyed. And it takes a lot of time to writing this equation into the form of LaTeX, because you're using the kind of this, it makes an interactive session. Okay, so that's it for this video, and I hope that you will be carrying out the next video. And also please access that full stack machine learning course. The link in the description box below. It is absolutely free with a handwritten, not a handwritten, I could say, the Jupyter notebooks with a lot more understanding. Means you can simply, after watching the video, can easily understand the Jupyter notebook. A real like programming assignment is also given to you in the form of Jupyter notebook for absolutely free. You have to go there, and you have to just link in the description box below, download a notebook, do the things, and summon in Discord server. Okay, and the Discord server, or in the comment box below, Discord server will be coming up soon. Okay, so that's it for this video, and thank you for seeing this video. Please be sure to subscribe to this YouTube channel, press the notification bell, and thank you for seeing this video. I will catch you in the next video. Till then, bye bye.